So, in the continuing from the last session, okay, we have completed the purely inductive circuit. Okay, we have completed the purely inductive circuit. Okay, so in purely inductive circuit, our finally the statement was that voltage leads the current. So this is my voltage, this is my current. Okay, so voltage leads the current by a phase angle pi by 2.
Right.
Okay. And then we had introduced a term called inductive reactance, which is equal to omega L, which is nothing but 2 pi by 2 pi FL. And then we found out the term IRMS, okay, which is nothing but your V by ZRMS. So this Z term is nothing but your like say this is actually this Z is your impedance. So in this case, because it is purely inductive,
it is XL.
so it is inductive reactance. Okay, so when it's next when we cover a combination of inductance plus reactance, it will become impedance. Okay, so now it is inductive reactance, which is nothing but so IRMS is equal to VRMS or VRMS divided by your XL. Okay, so what is Z will when we do LRC we will do what is ZL. Okay. So we if a typical household supply we know it is 220 volt, then we divide it by XL, which is equal to 2 pi FL, and then we found out the IRMS value. Okay. So that was the learning for a purely inductive circuit. Okay. Now we will do purely capacitive circuit. Okay. So we'll go a little fast because we'll cover almost capacitive circuit, then we'll cover LRC circuit,
and
then LC circuit. So because now we will be doing the like say CET paper or whatever, so we will not go deep into the derivation. So we will go as per the different formulas that are driving the inductive circuit, capacitive circuit, LRC circuit and all. So let me just quickly do what is let me quickly do the capacitive circuit. Okay. So pure capacitive circuit. Okay. Capacitive circuit. Okay. So so this is my circuit. Okay, so I have a capacitor here. Okay, so let's the capacitance is C or whatever. Okay, so this is my capacitance. So what happens in case of DC, the once you supply some voltage, you imagine this is AC. If it is DC, it will supply some voltage. Then on these two plates in capacitor, you know there will be two plates, and in between two plates there will be some dielectric and all. Then so one side there will be positive charge, one side there will be negative charge. So you will supply some DC voltage, then the charge will keep on getting accumulated, and after a certain point when it reaches the maximum value, then it will not allow the current to pass. Okay, that is for DC. Whereas for AC, like it is being written here, like so in DC circuit, when the capacitor is fully charged, the current in the circuit falls to 0. Okay, there won't be any current flowing to the circuit. That is for DC. Whereas for AC, when the capacitor is connected to AC source, it limits or regulates the current. It does not stop the flow of current. Instead, it regulates the current. Okay, but does not completely prevent the flow of charge. Okay. So the capacitor is alternately charged, discharged as the current reverses every half cycle. So the my current is going like it is sometimes it is positive, sometimes it is negative. So when this happens, my capacitors also it will be charged, discharged like that. It will happen uh, in AC the capacitor will get charged and it will get discharged like that. So okay, so that happens in AC. So so they are saying let Q be the charge. So let Q be the charge on the capacitor at any point of time t. So at any point of time let Q be the charge. So then the instantaneous voltage. So the instantaneous voltage in case of a capacitor is equal to Q by C. So that's you know that capacitance voltage is equal to
Q by V.
so we know C is equal to Q by V. In capacitance you have already studied. Okay.
Yeah.
So in case of AC, the instantaneous voltage is nothing but
Q by C.
Q by C. Okay. So this so then the formula for instantaneous voltage is Vm sin omega t, right?
Yeah.
So this is equal to Q by C. Okay. So then Vm sin omega t is equal to Q by C. Okay. Then again you know current is equal to dq by dt, right?
Yes.
dq by dt is means rate of flow of charge is nothing but your current. Okay. So if this is the case, then so your Q is equal to C into Vm sin omega t, right? Right.
Yes.
This is this equation when you do. So then Q is equal to this much. So I is equal to dq by dt. That means
C O.
d by dt of C Vm sin omega t.
That constant will come.
So when this happens, your I will become. So your I will become So this omega when you derive like omega will go out, right?
Yes. No. Omega.
Sin omega t. What is the differentiation of sin omega t? Omega cos omega t. Sin omega t. Omega. Yeah.
Omega cos omega.
Omega cos omega t. So the differentiation of sin omega t will this become omega into C into Vm into cos omega t. Right. This is the instantaneous current.
First you're supposed to take C Vm out, then differentiate it.
So C Vm are constant. You are taking it out, so it is C Vm into omega, right?
Omega
into cos omega t. Okay. So this you can write as C into Vm into omega into sin omega t plus phi. Okay. You know sin omega t plus phi is equal to cos omega t. Okay. But cos omega t plus pi by 2 is equal to minus sin omega t. But sin omega t is so from this what is your conclusion? Like now your current is leading with the current is ahead of voltage. In capacitance now you can see that current is ahead of voltage.
And voltage will lag by pi by 2.
So current is ahead means voltage will lag. Okay, so this is my governing equation. Okay, so my governing equation for a capacitive circuit is like I is equal to C Vm omega sin omega t plus pi by 2. Right?
Then it was Vm by XL sin omega t minus pi by 2.
So this is my governing equation. Okay, this is my governing equation, and here you can see current is leading. Okay,
voltage is lagging.
Current is leading means voltage is lagging. Okay. Okay, so and one more thing here is this voltage, this current. So this is IM actually. The RMS. Sorry, this is the max value. This is not RMS, so it is max actually. No. I is equal to, this is instantaneous. So instantaneous current is equal to, this is max voltage, this is max. So instantaneous current is this. So this this I, otherwise you can write as Im sin omega t Okay, so here this is Vm. Okay, so this is my Vmax value. Okay, so similarly this Vmax divided by this there is something called your, in this case Vmax Vmax divided by your ZC. Okay, so in this case Vmax divided by ZC,
which is X.
so Vmax divided by ZC is nothing but your Imax. Okay, so Vmax divided by ZC is nothing but your Imax. Okay, and here what is your ZC? ZC is your capacitive reactance. Earlier we were studying inductive reactance.
1 by omega c.
So this ZC is equal to 1 by omega c. Omega c. Okay. So 1 by omega c otherwise is 1 by 2 pi fc.
Capacitive reactance.
So this is your, this term is otherwise called as capacitive reactance. Capacitive reactance. Okay. So this term is actually we don't write it as impedance now.
We should write it as XC.
XC, right? You are correct. So this is XC. So this is XC. So when we are combining capacitance with inductance, then
it will be impedance.
Okay, so these are very important to remember. Okay.
Yes.
Bmax by XC is equal to Imax. XC is equal to 1 by omega c.
Which is 1.
And I is equal to Vmax into sin omega t plus pi by 2 into 1 omega and c. So this term actually, if you combine this is actually c omega, right?
Yes.
C omega. So c omega into Vmax into sin omega t
plus pi by 2.
Plus pi by 2.
So current will
So
be by
if
pi
you
by 2.
simplify it, it becomes Vmax divided by 1 by omega c, right? So this term. So into sin omega t into sin omega t plus pi by 2. So when you simplify this, actually this becomes this.
It become omega c.
So this whole
XC,
term.
sorry.
So this whole term is nothing but your Vmax by omega I omega c.
Which is Imax.
So this otherwise I can be, I is instantaneous current, which is equal to Imax into sin omega t plus pi by 2.
It is the same as inductive, but here it is omega t plus pi by 2, there it is omega t minus.
So when you compare this term with this term, okay, so your Imax is equal to
Vmax by XC.
Vmax by XC, which is equal to Vmax by 1 by omega c. So this is the term. Okay.
Yeah.
So now it is clear.
Yeah.
You should not forget it. You should never forget it. So from this, the first term is like my voltage. First we know capacitance is equal to charge accumulated by voltage supplied. Capacitance is equal to charge accumulated by voltage supplied. So V is equal to Q by C. Then if V is equal to Q by C, then in case of AC, this V can be written as Vmax into sin omega t, which is equal to Q by C. Okay, then we know current is equal to rate of change of charge. Okay, so this Q by instead of so you are replacing here Vm sin omega t, then your Q is equal to so I is equal to dq by dt. Then Q you have done as C Vm sin omega t. Here you have already found your Q as this. So I and relationship between I and V, how you are establishing it. So your aim is to establish a relationship between current and voltage. Then you will find the phase angle relationship. So I is equal to dq by dt then Q you have derived as C into Vm sin omega t. So then you put it here and then take the derivative of this. Omega goes outside, then this term becomes C omega into V max into sin omega t plus pi by 2. Then so that is your equation. So this V max divided by 1 by omega c is nothing but your voltage by your capacitive reactance. So voltage by capacitive reactance. So V max by capacitive reactance is nothing but your I max. So I becomes then.
That is actually general equation. V max by 1, V max by omega c.
V in case of a capacitive circuit, V is equal to I max into sin omega t plus pi by 2. So this is your
no, I is equal to I max, not V.
Okay. Okay, I is equal to, so what I am getting here, I is equal to I max, right?
I max right, or V max by X.
I is equal to I max.
Yeah, correct. You should write I is equal to V max by XC as general equation.
Okay.
You don't need to write it as I max. General equation is I is equal to V max by XC into sin omega t plus pi by 2.
Yeah. So,
because in inductive circuit we wrote I is equal to V max by omega L into sin omega t minus pi by 2.
Okay. So you are writing like your I is equal to V max by XC, right?
Yeah, that is general equation.
So that is the
V
equation
max
for
by XC is nothing but maximum current. But to write it in terms of reactance and voltage, we should write it like that.
So I is equal to V max by inductive reactance, capacitive reactance into sin omega t plus pi by 2. So and then if you compare it with the voltage,
the only thing difference is that pi by 2
so
plus
here,
pi by 2 minus
so V is equal to V max sin omega t, right?
Yeah.
But if you write I, it becomes V max by this term, which is I max, right?
Yeah, this
so
is I max.
So V is equal to V max sin omega t, I is equal to I max into sin omega t
plus pi by 2. Yes.
Right. So if you compare these two equations, you can find out, okay, the phase difference is pi by 2 here.
Yeah.
Okay, so you can take a snapshot of it. So here current leads, okay. In capacitance, in capacitor, current leads. In inductor, voltage leads, right? And that too by angle pi by 2, okay. So we can do again here, we can draw the Phasor diagram, okay. So if we draw the Phasor diagram, let us say this is my, this is this, and let us say this is my voltage, right. If this is my voltage, like let us say this is my negative axis, so if this is my voltage, okay, then some 90 degree, okay, so this is, let us say this is my 90 degree. So if this is my voltage, this is my current, okay. This is my current, so these are magnitude values, okay. These are my magnitude of the max values, okay. Then if this angle is my omega t, okay, this angle is omega t, and then then you know that if this is my V, then I can take the projection of this, and then this if this is omega 2 omega t, then this is pi by 2 minus omega t, then the projection will be like cos pi by 2 omega t. So so the instantaneous value will be the projection of current and voltage.
Yeah.
But if you see in the Phasor diagram, the current is leading the voltage by pi by 2, and you can draw that current and that time versus voltage and current, and you can draw those things. You can refer it later. Okay. So let us try to solve one numerical again on this. Okay. So the question is, yeah. So can you read it out, that question? What is the question?
A lamp is connected in series with a capacitor.
A lamp is connected in series. No.
This one numerical.
No,
Okay.
below one. Yeah.
Okay. A 15 microfarad capacitor.
Okay. The capacitance is 15 microfarad. Okay.
Is connected to a 220 volt.
Okay. Let me draw it. Okay. So this is my capacitor. Okay. Then this is 220 volt. Okay.
With 50 hertz source.
Okay, so the frequency is 50 hertz.
Capacitor is 15 microfarad.
Okay, then what is the question?
Find the capacitive reactance.
Okay, capacitive reactance is nothing but your XC, which is nothing but your 1 by omega C. Okay.
And the current.
Okay, so first question is find the capacitive reactance, which is nothing but, so let me write it here. Capacitive
reactance.
Okay, so this capacitive reactance is nothing but your 1 by 2 pi f c. So this C is microfarad, so you have to convert it into farad. 10 to the power minus 6 farad. Okay. So this become 1 by 6.28 into 15 into 10 to the power minus 6. Alright.
Yeah.
So this is, and then frequency. Your frequency is 50. So if you solve it, what is the answer?
212 ohm.
212 ohm. So this is your capacitive reactance. Okay. Then what is the next question?
And the current in RMS and peak value.
Okay. So current RMS and current peak. I RMS and I max. Okay.
Yeah.
So this your IRMS. So normally this supplied voltage is your VRMS, right? So this VRMS, IRMS is equal to VRMS divided by capacitive reactance. Okay.
Yeah.
So this
220 by 212.
This become 220 by how much? 212. Okay, how much is it?
1.04 ampere.
So 1.04 ampere. So this is one answer. Then they are asking what is the Imax.
Multiply into root 2.
So Imax is nothing but.
No, we have to find that is only Imax. Now we have to find peak value.
No, that is not Imax.
That is RMS. But peak means max.
So Imax is
root 2 times RMS.
I 1.04 into root 2. Okay.
Yeah.
So 1.04 into 1.414.
Yeah.
How much it is?
1.478.
1.47. So your Imax is equal to 1.47 ampere and IRMS is equal to 1.04 ampere, right?
Yeah.
And your capacitive reactance XC is equal to 1 by 2 pi FC is equal to how much? 212 ohm. 212 ohm. Okay. So these are your answers.
It's written current oscillates between 1.47 ampere and plus 1.47 ampere and minus 1.7 ampere and is ahead of the voltage by pi by 2. If frequency is doubled, the capacitive reactance will. There was another question. The question was if the frequency is doubled, what happens to capacitive reactance and current? So
yeah, that's right. So you can see the capacitive reactance. So your capacitive reactance XC is inversely proportional to frequency. Okay. So if your frequency is 2 times, so frequency is 2 times means XC will become half. Okay.
And what will happen to current?
So it will become half. So if your XC is becoming half,
current
your
will
current will double.
Because current is inversely proportional to XC.
Yes. So these you have to practice whatever CET questions are. Try to solve as many questions as possible using this governing formula. Okay. You can take a snapshot of this future reference. There is some
Theory.
some theory related to this. You can read it actually. So then after this we will do one LRC circuit. Okay. So whatever snapshot you are taking, that is for your quick reference. Okay. It's just in one picture everything is captured. Okay. So you keep those things and you can use it for quick reference. Okay. So we have finished your resistive circuit where current and voltage are in same phase. We have finished inductive circuit where the main takeaway is XL is equal to omega L and the voltage lags the current. Voltage leads the current in inductive circuit. In capacitive circuit, the capacitive reactance is equal to 1 by omega C and the voltage lags the current. Okay, 5 Okay, so now the more generalized, there can be LR, LC, LR, RC, that also can be there, but there is not much difference in LR, LC. Anyway, it will be pi by 2 phase difference, but in LRC the phase difference will be different. It depends on the relative magnitude of inductance and
Whichever
capacitance.
is more, it depends on that.
So the LRC circuit, okay, LRC circuit. So this is the more generalized one. So you can refer it. I am not going to go into the derivation of it. I am the main thing here is, like say, let me draw the circuit. So this is my circuit. So I have a resistor here. Okay, I have a resistor here, and I have a capacitor here. Sorry, I have an inductor here, a coil. A coil is nothing but an inductor, and I have a capacitor here. Okay, so I have resistor, I have capacitor, and I have inductor of inductance cell. So the governing equation, like we know that sigma V is equal to total voltage drop in a closed circuit is equal to 0 as per Kirchhoff's law. Okay, so so my supplied voltage, that is the instantaneous voltage, that is equal to V. Okay, so there will be 3 voltage drops here. Okay, so one voltage drop will be I into R, IR, right? That is one voltage drop. Another voltage drop across the capacitance will be charge by capacitance. The capacitance is equal to charge by voltage.
So V is equal to Q by C.
So B is equal to Q by C. Okay, so that is B is equal to Q by C. That is one, and then this the voltage drop across the inductance is equal to L di by dt.
Yeah.
So these are the 3 voltage drops. So your instantaneous voltage is equal to V is equal to addition of all 3 IR. Okay, so
V is equal to IR plus QC plus L di by dt.
Yeah, so it will be V is equal to IR plus L di by dt plus Q by C. Okay, so this is my governing equation, right? This is my governing equation. So you can refer to the derivation. I am not deriving, I am not going into the derivation of it. But finally, what I will get is like my max current is equal to, okay, I max is equal to V max divided by not writing properly. So I max is equal to V max divided by R square plus
That is impedance.
R square plus XC
minus XL whole square.
XC minus XL whole square.
That is impedance.
So that is square root. Okay. V max. Okay, so this is I max. So I max is equal to V max divided by R square plus XC minus XC minus XL square. Okay, so this term, this whole term, this term is called Z.
Impedance.
Z is equal to square root R square plus XL XC minus XL
whole
whole
square.
square. So this is my impedance. Okay. Then so that means I max is equal to V max by Z. So this term is called impedance. So these two terms are capacitive reactance and inductive reactance, and this term Z is called your impedance. Okay, so this is the key takeaway from here. Okay, so and the if you draw a phasor diagram, okay, if you draw a phasor diagram, how does it look like? If you okay, so if you draw a phasor diagram, how does it look like? So let me say this is my I, right? Okay, so let me say if let us say this is my okay. So yeah, so if this is my I or this is my voltage through the resistance. So let me say this is the current and voltage direction in the resistance. So I have a resistance. So this represents the current and voltage in the resistance. Okay, then my capacitance through the inductor. Okay, so this will be VL, right? If this is VR, if this is current in the resistor, my inductor voltage will be at an angle pi by 2, because whatever the current that is flowing in the resistor in the LRC circuit, the voltage in the inductor will be pi by 2 ahead of that.
Yes.
Similarly, just in the opposite direction, in another pi by 2 angle, it will be the VC, right?
Yeah.
This will be the VC.
That will lag by
Yeah.
voltage.
So the final phase angle of the resulting voltage will be what? So you imagine you are keeping the current direction as the reference. You want to see what is my resulting voltage. So that will be the angle of the resulting voltage with respect to the current. Okay, so it depends on the resulting value of the voltage in the voltage drop across the inductance and voltage drop across the capacitance. So if this voltage drop across the inductance is more, then the VL minus VC, this will be in this direction. So it will lead, voltage will lead.
Yeah.
But if your VC is less than VL, then voltage will lag.
Lag.
So it all depends on the relative magnitude of XL and XC, right? Anyway, because it is a series circuit, current will remain constant. Current will remain constant throughout. So only thing is the relative magnitude of voltage drop across the, like this is, let us say my voltage current flowing is I. So IR, and then this is say L di by dt. These are all same current. So let the current is the reference. With respect to current, what voltage, what angle the resulting voltage will make depends on the relative magnitude of XL and XC, okay, or the voltage drop across the inductance and the capacitance, okay. So that how do you get the phase angle in a LRC circuit? Okay.
Tan inverse.
So that is, yeah, tan inverse. So if you draw a triangle here, okay, so if you draw a triangle here, okay, if this is my triangle, okay, so this triangle, okay, say let us say this is R, okay, and let us say this is XL or XC or whatever, okay. So and then let us say this is my impedance Z, okay, right. So then my angle is phi, okay. Then my tan phi is equal to XL minus XC by R. So just remember your XL, XC, R all as unit ohm. So this is the formula for your phase angle. So you can refer the book for the like time versus voltage, time versus current, the Phasor diagram, all these things you can refer the book. But for doing quick numericals, this much is enough. This much of understanding is enough. Okay, right?
Yes.
Okay. So yeah, you can take a picture of this. Then you will go to the resonance, which is an important thing. So this resonance is like what is the principle of resonance in a LRC circuit. What do you mean by resonance in a LRC circuit? Okay, and that once we understand this, then we'll understand the principle of resonance in a LRC circuit. Okay. Clear now?
Yes.
Okay. So we have covered inductive circuit, capacitive circuit and LRC circuit, and the phase diagram and other things. Okay.
Phase angle.
Phase angle. Okay. Now resonance in LRC circuit. Okay. Resonance in LRC circuit. Okay. So you know my max current is equal to V max by Z now, right?
Yes.
V max by Z. Z is nothing but your impedance. Okay. So this Z you can write as V max divided by your R square plus XL minus XC whole square root. Right. So this is the equation for your maximum current. Okay. So when XC is equal to XL, okay, when XC is equal to XL, the current, this term will become equal to 0.
Yeah.
Right? If this term become equal to 0, your so your I max will be maximum. So I max will be maximum. Okay.
Become like resistance.
At resonance, at resonance, the I max will be maximum. So so this curve we like in vibrations. Here also we draw that curve. Okay, so you see like in the in the x-axis you have omega. Okay, so let us say in the x-axis you have omega in radian per second. Okay, and then let us say this varies from 0, and let us say at the center it is 1, and let us say at the extreme it is 2. Okay, see, this is the variation of current with the frequency. Okay, so here your curves will be like this. So at always at when omega the yeah, so your omega g, there is something called like when XL is equal to XC, at that time the resonance happens. Okay, so the question for will be the what is the resonating frequency. So when XL is equal to XC, it is the current will be maximum. Okay, so when does that happen? It's omega L is equal to 1 by omega C, right? 1 by omega C. That means my omega square is equal to LC, right? So that means my omega is equal to square root of LC. So this omega is otherwise
omega
called
square
as
is equal to 1 by LC.
1 by LC, you are right. Sorry, yeah, you are right. 1 by LC, correct. Okay. So 1 by LC square root. Okay. So this term omega, this is otherwise called as the resonating frequency, which is nothing but 1 by square root LC. So this is my resonating frequency, 1 by square root LC. This can be a numerical. Okay. What is the resonant frequency of a LRC circuit?
At resonance, XC is equal to NC. That is
at resonance, XC is equal to XL.
So from that you get this.
From that you can, or otherwise you can remember this. My resonating frequency is equal to 1 by square root L into C.
Resonance means the current in the
the
circuit is
resonance
maximum.
is when the current is maximum.
That is definition of resonance.
Resonance. Like in vibrations I have taught you, but you might not have remembered. I was teaching you forced vibration. So in forced vibration,
damped oscillation
so in forced vibration, your system will have a natural frequency. So if the forcing frequency is equal to natural frequency, your amplitude of vibration will be maximum.
Yes.
So comparing that mechanical system with the electrical system, their amplitude their amplitude of motion can be compared with the current. So this current again as a function of frequency you are writing.
Yeah.
There also the displacement you are writing in as a function of frequency. So that frequency is omega. Here also you are writing current as a function of frequency. So at resonant frequency, suppose when this omega becomes equal to omega 0, when omega become equal to resonant frequency, the displacement or here the current will be maximum. So this curve, the shape of the curve will be like this. Okay. So the shape of the curve will be like this. This will be one curve. Okay, so if we vary the resistance, I think for different resistance we will have different curves. So 100 ohm, 200 ohm.
Yeah, because inductance and capacitance will be same.
So two curves for two different resistance. Inductance and capacitance remaining same.
But resistance will be varied because other two is equal.
Yeah. So when this happens, so it will become a sharp curve like this, and finally it may become infinitive also. So it will be like for the curve will be like this. Okay. So at omega 0, the current will become infinite. Okay. This current will become infinite. This is for 100 ohm. For 200 ohm, it will be something like this. Okay. For 200 ohm, your curve will be something like this.
Unit of impedance is also ohm.
Yeah, impedance is ohm, reactance is ohm, everything is ohm. Okay. Okay, so this is okay. This is my 100 ohm. This curve is for 100 ohm. This curve is for 200 ohm, and this curve. Yeah, sorry. Actually, the lower one is 200 ohm. So more is the resistance, lesser is the current, right?
They're inversely
This is 100 ohm. So this resistance in mechanical, this resistance can be compared with damping coefficient. Okay. So if we compare mechanical with electrical, okay. If you compare mechanical with electrical, so there it was like, there it was displacement, right?
Yeah.
There it was displacement, okay, displacement, okay. Whereas in electrical it is current.
Yeah.
And frequency remains same in electrical, or this remains same. And there in mechanical it was damping or C, whatever. In electrical it
Displacement
is
or amplitude?
amplitude of displacement. Amplitude of displacement. Maximum displacement, that is, right?
Yeah.
Amplitude of displacement. So you compare mechanically with electrical like this. They are one to one. So this, okay. So displacement, current, and resistance, right? Yeah, so one important thing take away from this, when you are tuning your transistor. So earlier days you used to have a radio or the transistor. Okay, so that knob, that is nothing but a capacitor. Okay, so when you are rotating, like you might not have seen a radio in our days, what you used to do, you used to rotate a knob, that is rotating a capacitor.
Change frequency.
So by by rotating the capacitor, you are changing the capacitance. So the frequency will keep on changing. There will be a frequency of that wave which is coming. Suppose radio wave. See, the transmitting station will be sending a signal of a particular frequency.
Yeah.
If that frequency matches with this frequency, how we are changing that frequency?
Goes up to 10 power 6 frequency.
So
radio.
even that frequency matches with this frequency, you will have maximum current. So if current is maximum, you will be able to, like that, you will say that it has cut that frequency. That means what resonating frequency you are changing the knob, you are rotating the knob and varying the capacitance
to match it to
the frequency that is coming. So when it matches with the frequency, you will have maximum current or whatever.
Resonating frequency and frequency of radio wave should match so that you can hear.
You can hear. That's what the principle. That's
how radio is.
Radio, how to receive the radio signal. Okay. So this is about LRC circuit. You can do a lot of practice on this. Okay. And there is one concept called power factor. Okay. So so you can take a picture of this. Then we will discuss power factor, and then summarize things. So power factor in AC circuit. Okay. Okay, so what do you mean by power factor in AC circuit? Power factor in AC circuit. Okay, so so you know your in DC, let us say in DC, your power is nothing but your V into I, right? That's all. But in AC, your power is equal to is nothing but your VI into like I instantaneous. These are
I
both.
max, V max, sin omega t.
So you can write it as like say instantaneous V is nothing but your V max into sin omega t. Okay, so if this is the phase angle of voltage, the current phase angle will be different. Okay, it will be plus phi. Okay, in LRC circuit, in general I am telling you. Okay. So it will be I max into sin omega t plus phi. Okay, so I am telling in a general LRC circuit. Okay, in a generalized LRC circuit. In a generalized LRC circuit, there is a phase angle between voltage and current.
Yeah.
Okay. So this
if
is
it's from inductor or capacitor, that is different.
Yeah. No, it is a LRC circuit I am telling in general.
Okay.
See, if it is a only inductive circuit, it would have been pi by 2 direct.
Yeah.
Okay. But if it is a LRC circuit,
we cannot
it is omega t plus phi. Okay. So these two terms. So if you multiply these two terms, finally it will get simplified to like V max. It will get simplified to Vm. Okay. Vm into Im into cos phi divided by 2. Right. So these are max value. Vm into
this is power
Im.
factor.
Vm into Im divided by 2 into cos phi. So this 2 you can Vm by root 2 into Im by root 2 into cos phi. Okay. So Vm by this Vm by root 2 is nothing but your RMS value. Okay, so this is Vrms into Irms into cos phi. Okay. So this is the equation for power consumed in a AC circuit. Okay, it is nothing but Vi cos phi, V and I are RMS value. So power is equal to, so your power is equal to Vi cos phi. This is the equation of power consumed in a AC circuit. Okay. LRC circuit or AC LRC circuit. Generalized AC LRC circuit. Generalized AC LRC circuit. Okay.
Yes.
So this is the equation, but this is for AC. Okay, but for DC, power is equal to just VI.
VI is RMS value, not.
Here these are RMS value. RMS. So my household voltage is 220. That is RMS.
Peak is into.
I is also RMS. You should always use RMS only because that is the effective voltage or effective current.
Peak, if they are asking, they will ask separately for peak.
If they ask peak, then VRMS into.
We are always supposed to consider RMS.
RMS. Suppose somebody will ask what is the power consumed in your household.
220. That is RMS.
220 RMS. Okay. So this equation you have to remember, P is equal to Vi cos phi.
Yes.
Okay. So Vi cos phi. Okay. Or so this Vi cos phi, or otherwise you can write as P is equal to Vi cos phi. Or this V is nothing but your I into Z here, not resistance but impedance. I into Z into I cos phi, right? Which can otherwise be written as I square Z cos phi. If you know the impedance, if you know the current, and if you know the power factor, then you will find out the current. Okay. So this term phi is nothing but your power factor. Okay. This is one important term. Just you cannot multiply Vrms into Irms. You have to see what is the power factor. Okay. So there are some different cases. So in resistive circuit, there are different cases which are explained. Okay, so in resistive circuit, in resistive circuit, if the circuit contains only pure R, then phi is equal to 0 and cos phi is equal to
no
1.
phase
Okay.
difference there.
Then in purely inductive and capacitive circuit, that is called wattless current. Okay. So purely inductive or capacitive implies phi is equal to pi by 2. That means cos phi is equal to 0, right?
So wattless current.
So that means purely inductive and capacitive circuit give rise to
when
wattless
power factor
current.
is 0, then wattless.
Yeah. And in LRC circuit, your phi is equal to tan inverse
XL by X, XL minus XC by
right, XL minus
XC by
XL
R.
minus XC by R. So that is the in case of LRC circuit. And in LRC circuit, either you can use this formula I square Z, you can find out phi, you can find out
or
I
you can
square
use
Z.
pi cos phi.
Either of the formula you can use. Okay. So this is maximum power. Okay. So these are some of the governing different governing term. Okay. So you take a snapshot of it and then we'll do any method. Okay. We will do any method. See, these are you can you are taking the snapshot means you will follow it, you will remember it. You don't have to go through detailed derivation. Just see the snapshot and remember it. So just remember that phase angle this phi is equal to tan inverse XL minus XC by R. Okay, so that one actually by remembering this triangle. Okay, so this triangle in the x-axis you have R, in the y-axis you have XL minus XC, in the z-axis you have Z. Okay, so this angle is my phi. Okay, you just remember this. This triangle you have to remember. My base is always R, my height is XL minus XC, and my this H hypotenuse
You can also remember like impedance is XC minus XL, like square root R square. So for phase angle,
no, there can be a confusion whether it is R by XL minus XC or XC minus. So you should not confuse because
XL
R
and
is always
XC will always come together. XL and
and
XC.
that will come together. Whether it will be numerator or denominator, it can lead to confusion. So for that you should remember R is always as the base. Z is the H. Okay.
Hypotenuse.
And XL minus XC is the height. So XL minus XC is the height. That you should always remember. Or you can remember it like this. Always you think that my current is like this. Okay. Then this is like say my, let us say the VL. Okay. This is my VL and this is my VC. Okay. If this is the case, what will be my resulting voltage? That also, so you always remember this I means this is my resistive current. Okay, with respect to resistive, how are the other two? Okay. So you can practice as many numericals as possible so that you can solve any. These are very simple things. So you should never leave any of these things. So some quick formulas you should write down and remember, like this what I have told about this resonant frequency, whatever I was telling, that is also very important. Okay. Okay. So there will be 10-12 formulas in this chapter, but in science you should not remember only formula. That's why I had did all these derivations so that you can understand the each and every term what does it mean. Okay. So one numerical, a sinusoidal voltage of peak value 283 volt. Okay, so a sinusoidal voltage, okay, of peak value V max, right, is 283 volt, right?
Yes.
V max is 283 volt and frequency 50 hertz. F is equal to 50 hertz. Okay, is applied to a LCR circuit in which, so let me draw it. So it is like this. Okay. So let me say this is my resistance and let me say this is my capacitance, and let me say this is my inductance, this is my R, this is my C, this is my L. Okay. If this is a case in which R is equal to 3 ohm, R is equal to 3 ohm, L is equal to 25.48 millihenry, 0.48 millihenry, okay, and capacitance is equal to 796 microfarad, okay. Microfarad. Okay. So R 3 ohm, C 796 microfarad, L 25.48 millihenry. Okay, so these are the values. Okay. Find the impedance of the circuit. Okay. So what is my impedance? So impedance is equal to R square plus XL minus XC.
No, it is XC minus
square.
XL.
Okay, whatever. Okay. So this is my impedance. Okay. So R square is nothing but my 3 square. Then XL is nothing but my 2 pi F.
It is XC minus XL.
Okay, whatever, it does not matter.
Because you will get square.
When you square it, it will, okay, so 2 pi F into L minus 1 by 2 pi F into C. So you know pi, you know F is 50 and L you know. This millihenry you have to convert into Henry, microfarad.
10 power minus 6.
Yeah, so knowing this, if you solve, then you can find out your impedance, that will be unit will be ohm. Okay. And the next question is the phase difference between voltage across the source and the current. So,
tan inverse.
So the phase difference is equal to tan phi into XL minus XC by R, right? So that will be 2 pi F L minus 1 by 2 pi F C divided by my resistance, whatever is R. So if I know tan phi, then this term tan inverse, this term whatever it is. Okay, so that is the second part. Then the power dissipated in the circuit. So power dissipated in the
I
circuit.
square Z.
Yeah, so it is nothing but Vrms into Irms.
We'll find Z, so we can take I square Z also.
I square Z.
We found Z from here, so you can take I square Z also.
No, if you, I square Z phi, cos phi also will be there. Okay. So
Phi also we find.
You should never leave out the you never leave out the power factor. So as you said, the power is equal to I square
Z cos phi.
I square Z cos phi. Okay. So you know the phi from here.
Oh, for us voltage is also given, so we can use that other formula.
Voltage okay na, V Irms into Irms. Okay, Vrms into Irms into cos phi. So phi you should never forget. So you got the phi from here. Then your Vrms is okay. So they have given V max, right?
We don't know I.
Yeah, you can find out the I. So there is no problem in that. Okay. So you got your V max as 283 volt. Okay. So V max is 283, right?
Yeah.
So your Vrms will be equal to 283 divided by root 2. So this is your Vrms. Okay. Then what is Irms? So Irms is equal to Vrms by Z.
By Z.
Okay.
That which we found.
So Irms you have found out. Vrms you can find out by dividing by root t, and you know the angle phi, cos phi.
From that.
So from using all these things, you can find out the power dissipated in the circuit.
Yes.
And the fourth part is what is the power factor. So you know phi. So just remember that power factor is nothing but your cos phi. Okay, very important. Power factor is cos phi. Power factor is cos phi because finally I have derived that P is equal to Vi cos phi. So this power factor is your cos phi. So because it is cos phi, I am telling that purely inductive circuit or purely capacitive circuit is wattless current.
Because
that means
phase angle is
so this term is important.
in LRC it will be cos phi.
So we have solved one numerical, so you take a snapshot of it, then we will do the LC circuit, LC circuit, which is kind of a oscillator, okay. So you can say that power is equal to Vi cos phi or it is I square Z cos phi, Okay, so it is bi cos phi or I square z cos phi. Okay. So whatever snapshot you are taking, just refer it, so it will be easy for you. Because I am teaching you, if you refer it, it will be like, it will be easier for you. Okay, so we have completed the LRC circuit. Then we will do one simple LC oscillator. When we were seeing some CET paper, there was one question on oscillator. So we won't go into the details of derivation, but we will just say that what are the important formula. Okay, LC oscillator. So what is oscillator? Oscillator is a circuit in which you have a capacitor and you have an inductor. So you have an inductor and you have a capacitor. Okay. So when you have this, the governing equation for this is equal to what is the voltage drop. So there is no voltage source here. You just have a inductor and a capacitor. Okay. So the total voltage drop across this circuit is equal to 0. So that voltage drop across the capacitor is nothing but your Q by C. As you know, capacitor is equal to charge by voltage, or voltage is equal to charge by capacitance. And then voltage drop across the inductor is equal to L di by dt. Okay. So this is your governing equation for a oscillator. So this type of circuit is called oscillation. So it is some kind of oscillation, like it will, like when you use a spring,
Current
it will, like the charge will get accumulated,
Okay.
then it is charging, discharging,
because of
discharging.
capacitor and
Yeah. So it is kind of a oscillatory motion. In motion in spring you have studied oscillator. That means it will, when you pull a
To and
spring, it will simply go beyond the mean position, come back to the mean position, and then go upwards in beyond
Maximum.
the mean position, and then come back, and it will keep on oscillating. Suppose you have a spring, okay. So you have a mass here, okay. So let us say this is my original position, okay. So this is my mean position. This is my mean position. So I have just disturbed my spring, okay. So if I disturb my spring, it will come to this position, okay. So from center to this position it will come, okay. It will come, and then it will try to overshoot the mean position. So it will keep on oscillating between the mean position. So it will keep on oscillating. Similarly, in a LC circuit, the capacitor will get charged and discharged. So that is something similar, and this is the governing equation for that. Okay, so yeah, so therefore equation. Yeah, so we know, like Q by C, and I we know this is nothing but your dq by dt also, okay. So this becomes Q by C into d square q by dt square is equal to 0. So this is the governing equation. Then okay, so this is sorry, this there is a mistake there. L di by dt. Sorry, the L di by dt.
for
So this is L d square q by dt square. Okay. So this I can write as d square q by dt square. Okay. D square q by dt square plus 1 by LC into q is equal to 0. Okay, so what you can do here, like say
that q also you have substituted.
Yeah, so q by c is equal to L d square q by dt square.
Yeah.
Okay, so d square q by dt square is equal to q by LC, right? Right?
Yeah.
So okay, so in this case, actually this I is equal to minus dq
That
by
should
dt.
be minus.
No, this I is equal to minus dq by dt. That's why this become plus actually.
Okay.
See, this I is equal to actually minus dq by dt in this case.
In oscillator.
In oscillator, because when the current increases, charge decreases. When charge increases, current decreases. That's how it happens in the oscillator. So in this case, so d square q by dt square is equal to 1 by LC q is equal to 0. So this is the governing equation for a oscillator. Okay. So this can be compared with our normal spring. Okay. So what is normal spring? What is happening? So I am applying a force F, and there is a restoring force Kx here. So if I draw the free body, a force F is acting and a restoring spring force Kx is acting. So the net force is equal to F plus Kx is equal to 0, right? So F is nothing but your m into A plus Kx is equal to 0, okay? And we have done that x is equal to A sin omega t, right? So second derivative d square x by dt square, okay? That is the acceleration.
Yeah.
First derivative of displacement, so x here is displacement. So second derivative of displacement is your acceleration. So which is nothing but your, like say, first derivative, so let us do it. First derivative dx by dt is equal to omega cos omega t, okay?
Omega A cos
yeah,
omega.
so d square x by dt square
Minus omega.
is equal to minus omega square sin omega t.
A chaliye jo.
A, where is the A? Okay, omega square. Okay. So omega square A, omega square A, omega A, okay. So this become omega square A sin omega t. So this become otherwise minus omega square into x, right? A is nothing but your x. So this is nothing but your acceleration, right?
Yeah.
Acceleration. So you replace this value m into acceleration is omega square x, right? Plus kx is equal to 0. Okay, so this is minus. So m omega square x plus kx is equal to 0. So this becomes m omega square x is equal to kx. Right? This is the governing equation of a spring. Okay. So if x cancels, so omega square is equal to k by m.
Omega is equal to root
Omega is equal to k by m square root. So I will ask you this derivation. This is very, very important. Spring system, the derivation of angular frequency of a spring mass system, omega is equal to k by m. This is the one will get always confused. Okay, whether it is m by k or k by m, one should not get confused, because you can do the matching of unit also. See, k is nothing but force per unit displacement. Okay. So from that also you can find out, but just remember angular frequency is square root of k by m. So how I have derived, you have seen it here. Okay. So this is the free body. See here, this is my spring mass system. The mass, this mass is m. Okay. So I am applying a force F here. Okay. So it is getting, so the displacement is x here.
Yeah.
So this displacement is nothing but a simple harmonic motion. Okay.
Yeah.
So x is equal to a sin omega t. This is the equation, simple harmonic motion displacement equation. So if x is equal to this, second derivative of x is nothing but your acceleration, which is nothing but your minus omega square x. So you know this body is in equilibrium. Yeah. If it is in equilibrium, the net force acting on this mass, spring mass system is equal to 0.
Yeah.
So ma plus kx is equal to 0. So from here you have put a is equal to minus omega square x. So it is m omega square x plus kx is equal to 0. So finally you have found out my angular frequency is equal to k by m, square root k by m. So from this you can find out now time period and frequency. So what is angular frequency? Is nothing but your 2 pi by t is equal to k by m. So you don't need to remember so many things. If you just remember this, you can derive what is time period and what is frequency. Yes. Time period and frequency, 1 by time period is equal to frequency. Okay. What is frequency? Number of oscillations per second.
Yeah.
Okay, what is time period? Time taken to complete one oscillation, right? So, so yeah, so now this is our electrical equation, and this is from uh, yeah. This is one is electrical equation and one is your mechanical equation. We need to compare those two things and then find out what is the frequency of a oscillator. Okay. So my electrical equation is d square q by dt square. So you can see the similarity between electrical and mechanical. Okay. 1 by LC into q is equal to 0. Okay. This is your electrical, and your mechanical equation is, like say, yeah. So in the similar format, if you write it, d square x by dt square plus omega 0 square x is equal to 0. Okay. So how do I get this equation, if you ask me? Like say from here I can get it. Okay. So finally this my equation is yeah. So yeah, so this m into a is nothing but your d square x by dt square plus your k into x is equal to 0, right? So your d square x by dt square is divided by m, you just divide this side, right? K by m into x is equal to 0. Okay. So this k by m, you have got it like this. K by m is nothing but your angular frequency, right? So this k by m is nothing but square of square root k by m. So this can be otherwise written as d square x by dt square plus k by m is nothing but your omega 0 square, angular frequency square, into x. So you can call it as omega 0 because it is the frequency, angular frequency. Omega 0 square into x is equal to 0. So you are comparing the electrical equation with the mechanical equation, right? You are comparing. So your charge and displacement are same, and here
acceleration and
your charge and diffraction are same. Only thing you are comparing is your omega 0 square is equal to 1 by LC.
Which is resonance.
This is same as resonance also, what you have done earlier. So what you are finding now?
It is resonance only. Omega naught will be equal to 1 by root LC.
Yeah, so 1 by LC square root.
Which is resonance.
Which is not resonance. So in your test, there can be a question, what is the frequency of a oscillator? The frequency of a oscillator is nothing but square root 1 by LC. Okay? Clear?
Yes. Then transformer Vs Vs by Vp.
Then so at the end of your chapter there is 2-page summary. So I have taught you all these things. You can just refer the summary. You can discuss also. Only in 2 pages they have explained everything. So they have just summarized those points. Okay. Now that I have explained you, it will be just immediately you refer these 8-10 bullet points. It will be easier for you. Okay.
Yeah.
So okay, you take a snapshot of it. I will discuss those bullet points, so it will be easier for you. Just take a snapshot of this, then we will discuss those bullet points quickly. So done, na?
Yeah.
So we have discussed about oscillator and what is the frequency of the oscillator, right? So we have discussed about oscillator and what is the frequency of the oscillator, and how we are equating mechanical system with electrical system. Okay. So you know total energy of a system is equal to the kinetic energy plus the potential energy. So in mechanical system, let us say when we discuss about the total energy, okay, when we are discussing about the total energy, okay, so the in mechanical system, so let me say this mechanical system, my mass is m, my stiffness or the force constant is k, okay, and then my displacement is x, okay, and then my velocity is nothing but first derivative of displacement is dx by dt, right? Then my mechanical energy E is equal to kinetic energy plus potential energy, right?
Yes.
So my kinetic energy is nothing but half mv square plus potential energy, as you know, half kx square.
Yeah, in spring.
So how do you derive it? This potential energy, it is nothing but your, suppose this is your spring, okay? So you have a mass here, okay? So you are displacing the spring, okay? When you are displacing the spring, there will be a restoring force kx here, okay? So this kx into x and then the average value, okay? So this force, this is the work done, okay? So half kx into x and divided by 2, that average value, the work done will get stored as your potential energy, okay? So the total energy of the system is equal to potential energy plus kinetic energy. So in your spring simple harmonic motion, all these things are there. So total energy is equal to kinetic energy plus potential energy. Okay, so this is for mechanical system. For electrical system, yeah. So for your electrical system, what are those corresponding values in an electrical system? Okay. So corresponding to mass, inductance is your corresponding value, because inductance does not allow change of current, okay? So inductance is kind of an inertia.
It works on EMI.
So similarly, force constant is same as 1 by capacitance, force constant, and displacement is same as charge, okay? So it is same as charge. Current I is equal to dq by dt, and your total energy is equal to half q square by c, plus half li square. Okay, so instead of k, you are instead of m you are writing L, instead of velocity you are writing current. Okay.
Q square by C is energy stored in capacitor.
So
Li
this
square is
equivalent of velocity is current here. Okay.
There that energy thing, half QC square is energy stored in capacitor, half Li square is energy stored in inductor.
So this is the energy stored in inductor.
That is energy
this is
stored
the energy stored in capacitor. There can be questions like this.
This is from current, electricity and EMI.
Yeah. So yeah. So corresponding to mass you will have inductance, corresponding to force constant you will have capacitance, corresponding to displacement you will have charge, okay, because this is I dq by dt, I is equal to dq by dt, okay. So yeah, rate of change of, so that is same as, so displacement and charge are similar, and voltage and current are similar. So displacement is equivalent to charge, voltage is equivalent to current, velocity is equivalent to current, displacement is equivalent to charge, velocity is equivalent to current. Okay, then this is the energy stored in capacitor, energy stored in capacitor, and this is the energy stored in inductor, So this you have to by heart all those things, because you don't have time to derive in your test. Okay, so you will have to remember all these things. So total energy is the sum of kinetic energy plus potential energy, half mv square and half kx square. I have told how you got half kx square. Kx square is nothing but your force into displacement, and you are just dividing it by 2 to find out the mean value. Okay. So that's how the total energy stored in a spring. This is the total energy stored in a inductive capacitive circuit,
LC circuit.
Oscillator, in LC circuit. So these are all equivalent. So this is important. This oscillator LC circuit is a very important thing. Okay. Then transformer is simple
Same
one.
thing. We've
Okay,
done
then,
that. Directly proportional to number.
And then between forced oscillations and LCR circuit, there is a equivalent also that can be written. Okay. So forced oscillation, I had taught you forced oscillation. You may not be required to go into those details, but just remember, like in forced oscillation. Okay, that is the forced vibration what I have taught you. Okay. So there will be 3 forces. One is inertia force, one is damping force, and one is spring force. Okay. So 3 forces. The inertia force is nothing but your ma. Your spring, the damping force is c into velocity. Just remember, this is acceleration, this is velocity, and then the third term is equal to the spring force, which is kx, is equal to externally applied force, which is F0 sin omega t. F0 sin omega t. In forced vibration, there will always be external force always acting. In other derivation what I have done, that is free vibration. You don't have external force acting. But here in forced vibration, external force is acting. So this can be written as m d square x by dt square plus c dx by dt plus kx is equal to f0 sin omega t. So this is the equation for forced vibration, right? So there can be, so this generalized thing can be equated with LCR circuit. Okay. So what is LCR circuit? How it can be written? Instead of displacement, you can write charge. Okay. And instead of mass, you can write inductance. So you replace mass by inductance, and you replace displacement by charge. Okay. So L dq square by dt square.
Second derivative.
Second derivative. Then resistance, damping is otherwise compared with resistance. Okay, so here this is the damping. So this is capacitance, but you may get confused. So you put it as damping D. Okay, you put it as damping D. Okay, so this damping in a mechanical system is similar to resistance in electrical system. So here you can put it as R. Okay. So then first derivative of displacement, or this can be written as R dq by dt. Okay, R dq by dt. Then your x can be written as q, and k is nothing but your 1 by c is equal to the external voltage that you are supplying, the AC voltage. Okay, this is Vmax sin omega t. Okay, so this is the governing equation for a LRC circuit. Okay, so this is the governing equation for a LRC circuit. Okay, this is the governing equation for a LRC circuit, which can be compared with this. So this is the mechanical equation, that is the electrical equation. So this is the most generalized one. Okay, it may be too much for you, but you just take a snapshot of it, and then here you can go through.
I'll
this.
read that.
You read it. Okay, you take a snapshot of it. Then we will just quickly discuss the summary for 5 minutes. Okay. These are just snapshot, just to compare things. Okay. Otherwise, it should be enough to refer the snapshot. Okay. Okay. So you have transformer also here. You also have transformer. So there are so many derivations, but just you remember, like the
VS
primary
by
power
VP,
is equal to
VS by VP is equal to NS
so
by
if you have a
secondary called primary.
yeah, so you have this, then you will have so you have secondary coil. Okay, so this is this. Then your let's say this is primary, so this is Vp. Let us say this is secondary, this is Vs. The number of turn is equal to Np. Number of turn is equal to Ns. Okay, so just remember that the primary power is equal to the secondary power. If you assume that there is no loss, so that means Ip into Vp is equal to Is into Vs, right? So then this I. That means Ip by Is is equal to Vs by Vp, and Vs by Vp is equal to, just remember, Ns by Np. Okay, right? So Ns by Np. So this is Ns by Np. Okay. So if somebody asks the current relation also, you can find out the current relation. So the total power. So the main thing is the total power remains constant. But if there can be a numerical, they will ask, okay, there is 80% loss. That means if there is 80% loss, with this primary you will multiply that efficiency.
Yeah.
So, sir, if there is 20% loss, that means you have to multiply 0.8 here.
Okay. Because
Then,
that much.
yeah, that means 20% loss means 80% of the primary is going to the secondary. So let us say if there is a 10% loss, that means 1 minus 0.1 you have to multiply here. Correct? And what are the different types of losses in transformer? The flux leakage, hysteresis loss, resistance of the winding, eddy current, and here some of the losses. Okay, so that is about transformer, which is much simpler. Okay, so you can take a picture. Yes. Okay. So, okay, fine. Then I think we have we have completed everything. Just a quick recap of the summary. So, why we will take conversation? Just in 10 minutes, I will just give a quick recap of the summary. So, an alternating current, alternating voltage V is equal to Vm sin omega t applied to a resistor drives a current I is equal to I. So the current and so one is resistive circuit. First we have studied resistive circuit. Okay. In a resistive circuit, in a resistive circuit, V is equal to V max sin omega t. I is equal to V max by R sin omega t, and voltage and current are in same phase. That is one. Then we have the second point is I, capital I, which is nothing but your I RMS, that is the RMS value, is equal to I max by root 2. Just remember this. Similarly, capital V is equal to V RMS is equal to V max by root 2. This is another takeout. Okay. And then so in a resistive circuit, power is equal to VI or I square R or whatever. So that in a circuit with LRC it will be impedance.
Yeah.
Okay. I square Z into cos phi. If it is a LRC circuit, but in a resistive circuit, this is the formula. Okay. Then
inductive circuit.
So then we have studied about then inductive
Voltage will lead current.
so inductive, then XL is equal to omega L, and then voltage will lead current by pi by 2.
I is equal to V max by omega by XL into sine omega t minus pi.
Yeah,
General equation.
So here in inductive, Im is equal to I max is equal to V max by XL. Those things we have solved. Okay. So similar thing in case of capacitive circuit, voltage will lag current. Xc is equal to 1 by omega c. Voltage lags current, and I max is equal to V max
by
omega c. So this is another takeaway. So we have taught about inductive, then this is capacitive, then 0.5
LRC.
0.5 is LRC circuit. In LRC circuit, my max current is equal to V max
by impedance.
V max by impedance.
It is R square plus XC minus
Impedance,
XL.
that is equal to R square plus XL minus XC whole square square root. So this is for LRC circuit.
Then phase angle.
Yeah. So in LRC circuit there is something called phase angle, which is equal to XL minus XC by R. Okay. So that is the takeaway of LRC circuit. Okay. And then another takeaway was, like say, in a purely inductive or capacitive circuit,
phase angle is 0.
Phase angle is 90.
So wattless current.
No. Phase angle is 90. So that's why cos phi is equal to 0. So purely inductive or capacitive implies wattless current.
Phase angle is 0, so power factor is 0. Cos phi is 0.
Yeah. So that is point number 6. Okay. So similarly, just now I have told you that in a oscillator, so number 7, so in a oscillator, the frequency of a oscillator is equal to the resonance with resonating frequency
1 by root
is equal to 1 by root LC. Okay, so this is the frequency of a oscillator. Okay, then transformer we have done it. I said Vs secondary is equal to Vp is equal to Ns by Np. That is transformer, which comes from the conservation of power, and if there is a loss you have to multiply by certain factor. Okay, and there are some dimensions we need to know that okay, voltage has dimension volt, and so then its unit is its symbol is volt, and you can find out the dimension. Its unit is volt, current unit is ampere, inductance, reactance, inductive, capacitive, all unit is ohm, impedance unit is ohm, resistance unit is ohm, resonant frequency unit is hertz, and then power factor is nothing but your cos phi. It is dimensionless because cos phi is a value, it is dimensionless. Okay, so there is something called there is something called quality factor also. We might not have covered that. So there will be somewhere it will be there, that is called the quality factor. So quality factor Q is equal to, it is given as always R will be in the denominator, and on the numerator you will have omega L, or it will be if it is a if it is a inductive circuit, it is omega L by R. R will be in the denominator, and they say R into omega C. Okay, omega 0 into C. So this is called quality factor.
XC by R.
Either it is XL by R, this quality factor is XL by R, or it is XC by R. So XL by R or XC by R is quality factor. So in addition to power factor, there is a term called quality factor in RLC circuit. I just missed it. You just remember that R will be in the denominator. Either XL by R or XC by R
It's
is
not
called
LRC circuit.
quality.
It's purely inductive or purely capacitive.
Yeah.
Not in LRC.
So yeah, it is purely inductive. Yeah, you are correct. Yeah. Okay, so there are some more, other than that, there are some points to ponder like that is called thought questions. Okay, it means the points to thought, to think over it. So those are called points to ponder. Okay, so you can read and think about those things. So there can be objective questions on those things also. Okay, you just read those things. In addition to that, there are some 7.1 to 7.11. There are 11 questions. So you try to solve all of them. Okay.
And then I do CT.
You try to, before you no need to go into additional exercise. At least if you solve these 11 questions and if you show me, that should be good enough.
I'll do CT work.
Yeah, from CT or SIT, or this, first you do this. First you solve these 11 questions. Then you go to CT or SIT. Okay. Okay. Thank you. So you have completed alternating current completely. There can be 3-4 questions only.
Okay.